So now let's take a look at the implementation file for this abstraction, Vec. If you'll open up vim source vec.c, see that we've provided some scaffolding to get us set up. I've provided effectively implementations of some of the functions, and then for others in the operations, we've still got some work to do. All right? Before we continue on, what I'd like you to do is actually jump to the bottom of the file and check out this function, ensure capacity. And you'll notice that it's declared static. So this is a helper function that's only visible inside of this particular C file. And it's prefixed with an underscore. And this is often used as a convention to indicate this is a private function inside this file. And what I'd like you to do is describe in English what the implementation of this function is doing on Gradescope. And then once you've done that, come back to the video. All right, great. So we can take a look at the constructor of a vec, where we get a vec value back and see what it's doing very quickly. So this is a function that you're giving the capacity and the size of an individual item. And we initialize the members of our vec struct. Remember, we just list the order of those values in order. And you'll notice at the very end here for the buffer, I'm using calloc from the imported standard library to allocate and zero initialize the capacity number of items, and we're giving the item size, so that the size of each item. And remember, that gives us back a pointer to a block of memory that can store that many capacity elements of item size. And then after we initialize that, I'm applying the guard, and so we're checking for out of memory from our helper function in the guards.h file, and we're checking vec.buffer. So remember, when we are dealing with a struct value, we can use the dot operator to access its members. And then there are two curious arguments here, underscore underscore file, followed by two underscores, and then same with line. These are macros built into the compiler. The first one will evaluate to a C string, which is the name of the current file. So that would be source vec.c, and then the line number that this macro is run on is the line macro here. And so this allows the guard error function to be a little bit more specific and say you ran out of memory in vec.c at line 20, so that we know where it was in our program that occurred. Right? And so that's a common tactic. And then we just return that back. For the drop, pretty straightforward. We're freeing our buffer, and then we are resetting some of our members so that if we accidentally tried to use this again, this vec value after we had declared the lifetime expired, we would hopefully catch on to this being out of use and no longer a valid vec. Right? The accessors are as straightforward as you can imagine. You'll notice though here, as a reminder, because we are passing in pointers to vecs for all of our helpers. Remember, we're using the very first parameter of our functions are going to be effectively like you would think of the this keyword in a method call. We're going to pass in a pointer to the vec value itself. And so this will be the address of vec. And we're going to use the word self here as we move forward this semester rather than this, so that we can sort of disambiguate it from anything that would be set up automatically. This is something different, a variable, or I should say a parameter that we're using that's explicitly declared by us. And also, because we're using Google Test, and Google Test is C++ framework, as I mentioned, the this keyword in C++ actually does have meaning like it does in Java. So we don't want to use the this keyword when we start using Google Test, and we'll rely on the convention of using self anytime we want to refer to an operation on some abstract data type that will always be the first parameter that we pass in to one of these functions, right? So vec length, we give it a constant vector to ourselves. And just as a reminder, we use this const flag to say this is a read-only operation. We're not doing anything to modify this particular data abstraction vec when we use this function. Same with items, very straightforward. And then the three operations that we are going to implement next follow, right? And so the first is really just going to be about pointer arithmetic. How do we find a pointer to the index element item of our buffer? So we'll look at that in just a moment. And then how do we get data out of our Vec and set data back in at specific indices? And you all just looked through and figured out what was going on in ensure capacity. And hopefully this is pretty familiar looking code at this point. Here we're just reallocating if we run out of space and being sure that we do the bookkeeping of updating our capacity to reflect our new capacity rather than our old capacity, right? And what I'll point out here is there is some additional arithmetic that you inevitably noticed where when we do our realloc, we have to not only multiply the number of items we need, which we are just doubling the number of items that we think we might need based on the next allocation, and multiplying that by the size of an individual item. And this will make sure that we have enough storage space in our reallocated memory block for that. You could imagine we could want to potentially zero out any empty capacity that hasn't been assigned to yet. But for our purposes in this simple example, we're not doing so. So up next, we're going to try and implement ref, get, and set.